Pointer. Hi, my name is Suhail Azzedine. I'm from Lawrence Berkeley Lab and Lawrence Livermore Lab, and there's Tim Nifsey from Lawrence Berkeley Lab. And we welcome you for the first session of 2 sessions this morning on shallow and deep geothermal systems, characterization, integration, stimulation, simulation, and induced seismicity. We have another session this afternoon. All posters, just a couple of doors away from here. There's a slot that changed. There's a Woodron Talk 11.0-05. It's going to be replaced by Randy Sedgast, and he's going to talk about stimulation fracture, hydrofracture network in 3D utilizing HPC systems. Let's start with our first talk. It's an invited talk by John Kazu.
Thank you. Good morning, everybody. Pleasure to be here with you to jointly kick off the start of this year's AGU. And I'll be addressing experimental insights into CO2 water rock interactions in geothermal systems. My group has been doing experimental work and some field work looking at CO2 water rock interactions for a while now. And today we're focused on the geothermal. Much of the work I'm going to show you represents Caroline Laray's, a part of Caroline Laray's PhD work, and and some preliminary work from Jeff Martin's master's work. And then several students in the group provide a critical mass for ideas and insight and motivation. That includes, not listed here, Curtis Chopping, Virginia Markin, and Mary Kate McCarney. So today I'm going to deal with first, an experimental approach, just briefly field context, and also the design of the experiments, how they're built. And I'm going to spend most of my time on results and interpretations on the transition from water rock to water rock CO2 interactions as you might find in EGS systems and other geothermal and hydrothermal systems. Focused on silica, carbonates, and feldspar alteration to clays. And the approach I'm going to take is to stay out of the gory details of the experiments and focus on how the experiments provide insight and context to EGS. And of course, the carbon sequestration, and then I'll wind up with the summary. This is from the AGEA website. It's an EGS system. CO2 is not explicitly in it, but it serves our purpose. Cold fluid down and the blue, hot fluid out. And one can see that there's going to be fluid movement through the fractures, and our experiments emulate the water rock interactions at the front of the CO2 as it's first coming in. So if the blue represents CO2, water rock with CO2, supercritical CO2 in contact with that, and then of course at the margins as this circulates. I'm not addressing rock reactions inside of the wet CO2 itself. And our experiments for this talk broadly emulate the Roosevelt Field in western Utah. These are batch hydrothermal experiments. We run them at 250 degrees C, 25 megapascals, although the pressure does go up after we introduce CO2. We sample fluids in situ fairly intensely so we can define a reaction path for the fluid rock system. And we have a whole variety of experiments that we address. Fresh biotite granite with water, fresh biotite granite with a low pH water, which is analogous to an acid job on a geothermal system, which you might do to deal with some plugging problems. And then water and altered biotite granite, either deuterically altered or in vein minerals. Today's focus with epidote. Jeff is working on chlorite. I don't have all those, but some of those in the results here, and then we'll move on to calcite. So we do all these experiments with the water and the granites for about 1,000 hours, and then we repeat them, run them for another, we do a fresh experiment, run it for 1,000 hours, and into that one we add the supercritical CO2. We maintain that CO2 phase throughout the duration of the rest of the experiment, and that allows us to represent that cross-section that I showed you before. The waters in here emulate formation waters, so the waters are pre-mixed to approximately be in equilibrium with feldspars and quartz. So we're looking at a water rock that's starting fairly close to some sort of aged equilibrium system. So first results I'm going to show you on the classic rock alteration diagram. This is a diagram with quantitatively made famous in '69 by Helgeson et al. They looked at rock alteration in a granite at 3 and 200 degrees C. And it shows you the activity ratio, the activity of sodium and proton ratios against potassium and proton ratios. An important point here is you can document feldspars and their alteration assemblages. And the blue arrows I've got drawn here represent a collection of data points for the water rock experiments that I explained. So those blue arrows represent perhaps an EGS system where water is first introduced. And you can see that the arrows, the collection of points under them, represent the two feldspars reacting, heading towards a three-phase boundary where they'll settle into equilibrium with muscovite. Once CO2 is injected, everything flips around, and that's the red arrows down here. So the experiment, the water rock experiments are trundling along very nicely. CO2 hits, and there's an instantaneous, on the time scale of the experiment, and the sample is within 24 hours after injection, instantaneous, if you will, change. So the reaction path, instead of moving down and to the left in this activity space, is now moving up and to the right from the bottom left. And instead of reacting the two feldspars towards muscovite, now all of a sudden we're reacting the two feldspars and we're making muscovite, or in the case of the experiments, an illite, and smectite. So right away you can see if a CO2 EGS system is invoked, you've got to deal with the creation of smectite in these systems and the potential for pore plugging that goes with that. Now that last diagram was pretty classic, and it's in many geochemistry books and people are used to seeing it. It works very well for many granitic systems. In our experiments, we were also able to use a different sort of activity diagram wherein we're able to plot aluminum proton ratios against silicic acid. In the previous diagram, aluminum is conserved. In our experiments, we've got some pretty good aluminum data, so we didn't have to deal with conserving aluminum. We could look at it moving around in the system. And so what we've got on the left is a diagram that shows the evolution of water rock, analogous to granite water in EGS. And on the right is how activity space shifts when you add CO2 to that water rock EGS system. Here on the left, we have a big smectite field, small calcite field. In between, we have things like zeolites. And all these blue paths and fields with the data underneath them represent the different reaction paths of those different water rock systems I showed you. So underneath all that, there's a diversity of movement related to, there's water granite reacting here. In fact, this big blue arrow is the low pH water granite system evolving up. There's water granite epidote, which starts out more luminous anyway because of the epidote. And the other paths take a diversity as well. Here on the right, on the CO2 diagram, you can see the big field of CO2 crowding out everything and the big field of smectite. Again, you get a jump when CO2 hits that ongoing water rock reaction system, and you get a jump up to the top right to where all that data is with that red arrow. And all the experiments fall on that red arrow. Everything shifts up to the right and stays on that rock solid straight right arrow, and instead of evolving up, we're now evolving down. What happens is when CO2 hits the system in the lab, and by analogy in an actual EGS operation, the CO2 is going to take complete control, at least initially, of the fluid rock reactions. And that's true whether you've got pure granite, fresh granite, altered granite, whatever. Everything pops over and will react the same way after CO2 hits it. And what that means, from practical purposes, is that you can do a field test, an EGS field test with CO2, and you should be able to apply it to a wide diversity of granite geothermal systems. Now, we still have some work to do to maybe chart some reaction space up here and up here to make sure things are still moving around wide up here and still track to that red line here. But at least initially, the hypothesis is that one field test, well selected, can represent a wide variety of granitic rocks and their waters. So that's the first important point for EGS on this diagram. The second important point is calcite. Once CO2 hits, calcite becomes more important, and that's because its stability field gets much larger. However, none of the data points actually reach the calcite field. So even though we have CO2 in there and we're evolving towards calcite stability, we never quite touch it. We almost get there, but not quite touch it. When we do make calcite, however, is not in situ with the ongoing water-rock CO2 reactions. When we do make calcite, it's when we degas, when we quench the experiment and bleed off the CO2, then we precipitate calcite. Taking that over to an actual EGS operation, what it means is that with CO2 ongoing in the operation, if there's any residual water in the system on the margins, say, one doesn't have to worry about calcite precipitation, at least not initially. So there should not be a pore plugging problem from that. However, if there's CO2 loss, either through some sort of system failure or degassing or maybe at the end of the operational life of this thing, then calcite can precipitate. That could be a bad thing if you're worried about pore plugging. That could be a good thing because calcite precipitation, possibly in concert with the smectite precipitation I showed you before, if tuned properly, could be a seal. You could almost imagine engineering a seal to leave in place the CO2 that you've reacted behind and walk away and take some carbon credits at the end of the life for sequestration of your CO2 EGS system. But during its life, you're not going to be mineralizing the CO2 and being able to take credit for that. And the other big take-home point from these diagrams is how everything evolves over, whether it's on the water rock side of things or on the water rock CO2 side of things, everything evolves over to where silica concentration in the waters are controlled by the solubility of chalcedony. So the feldspars are reacting, they're dissolving, they're releasing silicic acid. Quartz kinetics are slow for quartz precipitation, so you can put silica into solution. We're too warm for amorphous silica to control silica's solubility. And just for reference, that's right up here. If we were down at 25 degrees C, we would be on that line. But at 250, we're stuck on this line here, on the chalcedony saturation. So what that means is, at least on the EGS operation with just water, where there may not have been elevated silica levels before, just by virtue of the feldspar reactions, you're going to elevate silica levels. And of course, silica scales have always been a problem in the geothermal industry, and so this is an alert to watch out for it here too. And that also translates over to when CO2 is in the system. CO2 is not going to elevate, interestingly enough, CO2 is not going to elevate silica concentrations beyond what just the plain water rock will, because chalcedony is the barrier. Nothing gets more silica rich than that. So there's a lot of take-home points from some experiments that can be used to guide the field tests on these EGS systems, or the siting of these EGS systems, and maybe even the modeling of these EGS systems. And what these experiments show is that we're having to deal with the balancing act of fluid rock systems. In an EGS, maybe where there was no water initially, with a granite, and then when water hits it, there's a tip in the balance, and nature is going to try and restore that balance. Or if there's already water in the system and there's different waters coming in, the balance is tipped, and the water rock reactions are going to go to try and get that balance back to horizontal. But when CO2 becomes a player, it's not a simple two-sided teeter-totter anymore. It's a three-sided teeter-totter. And you can imagine a pivot point right in the center underneath that three-way teeter-totter where the water and the rock and the carbon dioxide are jockeying for position to balance these things out. And at least initially, early on, the carbon dioxide is the big player because of its sheer mass and existing as that immiscible phase. And then as it over time, the rock and the water will reassert their control. So to sum things up, there can be a diversity of reaction paths, in other words, evolution, water rock evolution of different granitic water systems, but those become uniform once CO2. Reaction paths converge, and moving forward, many different systems will behave very similarly. Calcite does not precipitate while CO2 is an active part of this system, but can if there's degassing or later on in the CO2 EGS. Feldspars dissolve incongruently, and that's well known, but in the case of the water rock EGS system, it's making illites and micas. In the case of adding CO2 to it, it's making smectites in addition. And then you've got to worry about introducing silica saturation due to the incongruent dissolution of feldspar, and that silica is controlled by chalcedony. This work is supported by a DOE grant in concert with our collaborators at the University of Utah and some scholarships to Caroline LeRae, and I thank you for your time.
Any questions?
I have a question. So, how would you, was there a question out there?
Yeah, go ahead.
Okay, how would you cause the calcite precipitation in order to trap CO2 at the end of the EGS lifetime?
Well, you're going to have to degas the CO2, so you can imagine sort of using a heterogeneous formation and maybe in an upper layer flood it with CO2 and then degas it, and then everything under that might be where you might have the actual EGS operation.
Please.
Yeah, somewhat related to that question. You mentioned degassing promote precipitation. Could you say something about the time scale of that precipitation?
That's fairly instantaneous. I mean, it's pretty well known. You get degassing in well bores, oil and gas industry, geothermal, and calcite drops out pretty rapidly. On the time scale of these experiments, it's hours. You can make calcite within hours, very beautiful calcite crystals within hours.
Thank you. We'll move to our next speaker. It's Bill Boursier, myself, John Hunt, and Roberts. Bill Boursier will not be here, so I'm going to give his talk. So I'll be talking about enhancing the sustainability of enhancing geothermal systems using colloidal silica gel. This is the outline. I will give a brief motivation and the relevance of the project, why we are using silica gel. I'll show some experimental results. There is a poster this afternoon dealing mainly with the experimental study. And then I will introduce the numerical model that we're going to use, and I will ask a couple of questions. How the silica gel can enhance the thermal extraction, reduce the water uses, minimize the short circuiting, and apply it to conventional geothermal systems. Several reports have been published in the last 5-10 years displaying all the roadblocks to popularize the EGS in different applications. And most of the problems are related to fast block in the fast pathways, specifically short circuiting, enhancing the heat recovery by enhancing the sweep surface, and then minimizing the water losses to the surrounding formation. For example, in the geysers, they use about 1.5 million gallons a day to sustain the extraction in their geothermal systems. Interestingly enough, Lawrence Livermore Lab had a few patents about extracting the silica gel from the brine geothermal. Bill Boursier has extensively worked on this problem, so we decided why not try to use it as a blocking or a diverter agent for enhancing the geothermal systems. So colloidal silica, it's very inexpensive. It's environmentally friendly. It can be removed by hydraulic mitigation. The gelation can be triggered externally by changing the pH, for example, and it has fewer environmental restriction, and therefore that will alleviate the permitting process. So here's what we are going to do is to try to see the suitability of the use of silica gel for zonal isolation and diversion, and to try to manage the water losses to the formation. We are trying to use a combination of the experimental work and then the numerical work. Here's a summary of the experimental work. we conducted several experiments using rheometers, and we determined when the gel mature or become solid in some ways as function of the concentration of the silica, the concentration of the SO2, and then the ratio between the chlorine and the sodium. And we obtained a regressed formula such as the one presented here. So it's the log of the time gelation as function of the different concentrations that we are playing with. So having that law, we can implement it in a code that we have. And this code does a stochastic discrete fracture network with several hydrological processes. So we took this code and we modified it in order to add a non-Newtonian flow. We have the density changes as function of the concentration of the silica, the temperature and time. Thermal conductivity changes to the heat capacity, viscosity, and so on. And it has also a loop on the feedback of the changes of the permeability due to the position or the maturity of the silica gel itself. We started with 25 degrees Celsius. We extended to 150 degrees Celsius. It has a multiphase formulation, etc. So an example on how to apply it to enhance the thermal extraction. Here we are showing, where's the pointer? Here we have an injection well and an extraction well. It's here the case of smooth fracture, and here it's a rough fracture aperture. And these are pretty much the streamlines as well as the pressure field in both cases. Then after about 80 days, we realized that the temperature is decreasing, and we sent the slug of gel for about 10 hours and let it gel. That gelation created an obstruction of this kind, which allows for the streamlines to move around it, and therefore harvesting the heat from a virgin rock than the one that was previously harvested. And that shows you that there is a rebound on the thermal extraction itself. For the emplacement of water, so we have an injection well, an extraction well. We send a slug of gel. We let it develop over time. After a certain time, the gel was matured, and then we start extracting from the second well, and that shows you how you can create an inner loop with a closed system, so therefore every water that you inject here, you can recover it without loss to the formation. We've done the same thing for a rough surface and gives you similar results. So to remediate the short circuits, I'm giving you here a short a cross-section, a vertical one, an injection well, extraction well. There are a few fractures that they intersect this rock, this first injection well. One of them create a short path between the two wells, while the other one is hidden. Actually, you will not be able to characterize it through the well, and it's connecting the neighboring area or the vicinity of the two wells. So we do an adaptive mesh-refined finite element solution for the problem that allows you to mimic all the flow and subsurface transport within the formations as well as with the fractures. We also solve for the streamlines to make sure that we capture all the mixing at the intersections of the wells. This is a very difficult problem to solve. And here's an example. So this is without the application of silica gel. This is with deployment of silica gel. These are snapshots as function of time. So initially you inject through this first well. So you see that there's development through the first crack. And then the second crack, because it's higher hydraulic conductivity, there's more water goes toward it, and then development of the process. And you can see there's some cold water reached already the extraction well. If we go and packer the lower zone, so you can do this with a tracer test, actually, with multi-level sample and here system, you can determine what's going on. So you go and packer the bottom area, you deploy the silica gel, and then you re-inject the tracer, and you can see that the second fractures pretty much disappeared. There's still some leakage but not enough to decrease the temperature at the extraction well. The third application was to see if we can use this for conventional reservoirs or geothermal reservoirs, injection well, extraction well. This is setup of the domain. So again, you can see the deployment of the silica gel. The ring gets deployed. We don't have a closed system here, yet there is enough perturbation of the flow system to create a diversion of the streamlines that therefore harvesting a region that is hotter than the colder one. Here's an aerial view of the streamlines. So there is no extraction. There is no extraction development. So this is a 3D. There's the shell where the silica is. And then after a while, it starts gelling. You extract, and there's the diversion of the streamlines, and you capture even further more hot water. This is the summary. We tried to progress in two fronts, the modeling and the experimental as well as the utilization. I'll be more than happy to entertain any questions.
Are there any questions for Suha?
Please.
Maybe I might have missed it, but could you mention something about the size distribution of these silica gels?
Actually, the colloids that we're using, they're about 10 nanometers. And so we're doing the same experiments using 50 nanometers because the gelation time depends on the surface area. So we're creating different model of gelation time as function of the diameter of the colloids. So those are 10 nanometers. Any other questions? All right.
I have a question.
All right, please.
When you established your model, you have a list of parameters for example, the plugging of the fractures. How many of those parameters do you have good models to justify, or are there more measurements that are required?
Actually, most of those parameters are available because it's a thermohydrology problem. So I have pretty much everything that I need except some of the thermomechanical properties of the silica gel themselves. So in case when I create that cells and I want to force it to break it so I can use a larger surface, I don't have yet the mechanical properties of the silica gel themselves. But the thermohydrology as well as the chemistry, we have a good control of the numbers. All right.
All right.
We'll go to the next. So our next speaker is John El-Khoury, and he's from the University of Irvine.
Can we click back? Can we go back?
Go down to the
All right, everyone. Thank you so much for coming at this time today. Today I will share with you some lab experiments that look at geothermal energy recovery from sedimentary formation. And this work is in collaboration with Russ Detweiler from UCI and Michael Bruno and Vahid Sirajian from Geomechanics Technologies. As you know, today's session is shallow and deep geothermal systems, and our work is focused on studying deep and shallow geothermal systems, but in sedimentary formations. And the reason for that is because sedimentary formations, they provide many advantages over traditional EGS fractured systems. And some of these advantages we could mention, like reduction in risk for induced seismicity, elimination for the need of hydraulic fracturing, reduction for surface water disposals, contribution to the decrease in greenhouse gases, and as we learned today in the first talk, also potential usage for CO2 sequestration as well. And added to this advantage, these advantages, also new advances in horizontal drilling allow us to apply these technologies from the oil and gas industry to these geothermal systems and sedimentary formations. So our work, as I said earlier in the title slide, is focused on lab-scale circulation systems and aimed at quantifying the heat transfer capacity of sedimentary rocks. So we do these experiments, we try to characterize the heat transfer of the sedimentary rocks, and then we use these experimental results to validate numerical models that try to represent the lab experiments. Then, once we have these models validated, we extend our numerical approach to field-scale simulations. And just to mention that these models were done using the well-known TUF2 code. So our lab experiments are motivated from the field-scale concept. So you saw earlier today some slides on geothermal systems, and here we get the concept of the pairs of wells, horizontal wells going into sedimentary formation. When we might use a binary cycle or not in here, but the idea is you inject the fluid, they heat down here and they come up here in this system. So this kind of a pair well system has many different parameters that one might try to study. For instance, the separation between the wells, the injection sequences of the fluid in it, and so on. But we use this concept to motivate our lab scale experiments. And basically what we do is we take a region around the wells, simulated here by this disk. We heat it around its circumference, and we inject cold water in here, and hot water comes out of the sides. And just to show you the connection with the lab experiments, here is a picture of our sample. So here is the sample down here. It's sandwiched between two end caps. These are thermally insulating Teflon caps. So this set of experiments I'm going to share with you today looks at two kinds of samples. One is an intact sample. As you see in here, we have two wells where we inject and produce the fluid. And also we compare our results with a fractured system in which we have imposed a fracture short-circuiting the two ports in here. As you can see highlighted very nicely in here. Just to mention that these two samples are the same. So what we do is we take the first sample, we run our experiments. Once we're done, we fracture the sample so we can compare exactly only the influence of the fracture connecting the two ports. Before I continue to the experimental results, allow me a couple of slides to share with you some of the steps that describe the experimental setting. So here is a top view cross-section of our experimental setting. So in this area here, we highlight the sample. As you've seen earlier, we have the two ports for the inlet-outlet fluids. We jacket our sample. Then we have a heating tape surrounding the sample that's controlled temperature. Then we have a confining fluid between the sample and the vessel wall. And as you can see, we have many aspects of it controlled, like the temperature monitored, we have the confining fluid, and feeding for the heating tape. Another important aspect to realize here is the cross-section and section view for the sample. And I would like to point out here that an important aspect to keep in mind are these two points in here inside the sample where we measure the temperature. So later on I will show you some measurements of temperature as a function of time inside the system, and when I refer to inlet and outlet temperatures, that means temperatures measured at these 2 points. So remember, fluid comes down at the inlet, flow through the sample, and comes out here at the outlet. And just to share with you some of the length scales here, for our system, you can see the sample has about 23 centimeter length scale in here, almost 4 centimeter in height, and we use 2 Teflon layers as I discussed earlier for installation. And here's our experimental setting. So first we start with a vessel where we have our sample. It's thermally insulated. And as you can see, there is fluid coming in here, comes out in here, and we measure those temperatures as I mentioned earlier. We control the confining pressure in the system very carefully. We also control the temperature, and we monitor the heat flow into the system that provides heat to that heating tape I referred earlier. Then the flow coming into the sample is also controlled, so we have a continuous flow mode. Basically, we can run this forever, as long as we have enough fluid in the reservoir up here. And to make sure that the inlet fluid is controlled in terms of its temperature, we run our tubing through a constant temperature bath. So that assures us that the temperature of the fluid coming in is constant. Then the fluid comes out, we have a back pressure regulator that controls the pore pressure in the system. And finally, we do have, besides having pressure transducer in all these pumps here and here, we also have pressure differential measuring at the inlet outlet like this. So once we have cleared this experimental setting, now I will show you some results of temperature measured at the inlet and outlet. All right, so this is an example of a temperature measurement. So initially we have the boundary temperature at a constant value, and the inlet-outlet temperatures are very close to it. When we initiate flow, then the temperature decay as we expected. Here is the outlet and inlet temperatures. So we have a drop as we expected. There is a time scale associated to it. It's very different for the inlet and the outlet. Also, we observe some delay in the inlet and outlet drop. So basically, the inlet temperature drops first and then takes some time for the outlet to drop as well. We have steady state values after a certain time. We vary the flow rate. So in this particular example, it's, I believe, 10 milliliter a minute. So we vary those flow rates. We also vary the boundary temperature. At this point here, we have almost 120 degrees. We vary that as well. And as I said earlier, I showed you a picture of two samples, intact and fractured. So right now, I'm going to try to show you the result from those two samples and compare the effect of the fractured system. So once we are familiarized with this kind of behavior, I will move on for the first results for the intact samples. So here is an example where we have on the top here, it's the flow rate. It goes from 0 to 10 milliminute in this case. 10 represents 10 milliminute for the flow rate. The temperatures at the inlet and outlet inside the sample, they decay like in this fashion. So we run for smaller flow rates and higher flow rates. And just for reference, down here we have a dashed line representing the inlet water reservoir. So this is the temperature of the water coming into the system. And for these experiments, I have some of the parameters discussed down here on the sides. Confining pressures, 150 psi, pore pressure, 100 psi. Range of small pressure gradients, and that's due to the fact that this sample is fairly permeable, as you can see in here. So now once we have this system described like this, now I'm going to move to the fractured sample, where we'll see similar results, but definitely the steady state values are going to change, of course. And here is it. So it's basically similar behavior, but the steady states have changed. So now once we have this set of experiments, we would like to look at some parameters that we can describe them. So for instance, for today, I'm just going to focus on the steady state temperature, given the limitations of time, of course. So I will look at these values of steady state temperatures as a function of the flow rate for these two experiments. And here it is. So basically here I'm plotting steady state temperatures in red for the intact sample and in blue for the fractured sample. Of course, there is no surprise here, as you would expect. If you have a fracture that short circuits the system, but provides flow path between the inlet and outlet ports, you will have less heat extraction. But what we do here is we quantify that difference. And as you can see, there is almost 20% difference between these two. So basically, this argues for a sedimentary system against a fractured system where you would have much more porosity and you would have much more possibility for extracting heat from the system. Now I'm going to move on to a next set of experiments. So basically here I showed you earlier experiments at 120 degrees C for the boundary temperature. But also we did many other experiments at different boundary temperatures. So here at the vertical axis I show the outlet temperature, that's the steady state. And the horizontal axis I show you the boundary temperature. And we've done them for different flow rates, as you can see, for 10 and 25. And we see very clear correlation between these two parameters. This is the case for the intact rock, and also we did it for the fractured rock, and we see exactly the same thing. So this description allows us to extrapolate our results beyond our experimental conditions. For instance, we can predict higher results for higher boundary temperature, and also for other flow rates that we had not considered in our experiments. All right, so having some of these experimental results, now we move to some preliminary numerical simulations that we did, mimicking the setting of the lab experiments, using TUF2 as I mentioned earlier. So here I show you snapshots as a function of time of 2D maps across the sample from the top. And you can see for this particular case, it's 100 degrees C boundary temperature. You can clearly see the inlet and outlet ports here of the sample. As time goes by, you develop this front that gets to a steady state where you have this temperature distribution inside the sample. So now once we have these kind of simulation, we would like to compare them to the experiments. And here is one of the first comparison we did. Of course, we adjusted the temperatures, the permeabilities, and we used some numbers for measured numbers for thermal conductivity and so on. And here it's very nice that we can see the comparison between the experiments and the lab experiments and the simulation. Lab experiments are the red and blue curves for the outlet and inlet temperatures, and the simulation are the dashed lines here. So we do fairly well, very good job in matching these experiments. So now once we have these numerical models that match well our lab experiments, we can move on and to numerical simulation at the field scale. We also did some simulations with the fracture, but in the interest of time, I'm going to skip on those for now. So as a summary, so we have performed detailed fluid flow experiments in hot and permeable sedimentary rocks at the lab scale under varied thermal, mechanical, and flow conditions. For instance, here I list few. So temperatures, we've gone from room temperature up to 120 degrees, flow rate over this range from 2 to 50, confining pressure as well, over an order of magnitude, pore pressure as well. And as I showed you today, we looked at intact and fractured samples. These experimental results show clear dependencies on flow rate and boundary temperatures. So we could exploit those properties to go beyond our experimental conditions and have possibilities of getting values for higher temperature, for instance, of a larger range of flow rates. Preliminary numerical modeling show good agreement with our experiments, and this points at the potential of extending our models to the beyond experimental scales and conditions, so basically going to the field scale. And basically, finally, the idea is that our combined lab experiments and numerical simulations point at the potential for geothermal energy production from hot sedimentary formations, and particularly in the binary cycle, as I mentioned in the first slide, because we can go to sedimentary basins that have lower temperatures, and with the aid of the secondary, with the binary cycle, we can extract the geothermal energy. And finally, I will leave you with some pictures from the lab setting. Thank you very much.
Any questions? We have time for one question. Please.
Yes. So I have some tables here. Sorry. So let me go. Can I go back down? Yeah. So here are some of the numbers to share with you. So for thermal conductivity, for heat conductivity, we use between 2 and 3.7 watts per meter centigrade. For the permeabilities, you can see the numbers right there. So this basically, we explored a range of numbers. But the permeability that we used for the results I showed you, those were based on permeability or measured permeability. So basically what we do, as I said earlier, we measure pressure differentials and flow rates. And from those, we infer permeabilities, and that permeability we use in the numerical simulations.
go to our next speaker. It's Stuart Walsh from Livermore Lab, and he's going to talk about HPC simulation for grain scale spallation to improve thermal spallation. I'll give you this guy here. You can work that one.
So today I'm going to be talking about some work that we at Lawrence Livermore, myself, my colleague Ilya Lomov, have been doing in conjunction with Tom Weidman and Jared Potter at Potter Drilling. We've been looking at developing some numerical models to simulate a process of thermal spallation with the idea of improving their thermal spallation drilling technology. The reason that we're looking at this is in order to help reduce the costs associated with producing engineered geothermal systems, in particular the drilling costs associated with those. So in the US, we actually have quite a bountiful supply of EGS resources, and what's more, as we all know, EGS provides clean, renewable, and importantly, baseload energy. So a constant energy supply similar to what you would get from a coal-fired power plant or a nuclear power plant. In light of this, then, we might want to ask, why is it that EGS resources are not more widespread? And the answer to that, or at least one of the answers to that, is the costs associated with producing and developing EGS wells. EGS resources are typically fairly deep underground, so we have to drill a long way, and what's more, we have to drill into hard granitic basement rocks, which are difficult to penetrate with traditional mechanical drilling technologies. So the take-home message is, if we want to see more widespread use of EGS, then we need to come up with new drilling technologies to help reduce the well costs associated with EGS. And that's where this idea of thermal spallation comes in. Mechanical means are not the only techniques for penetrating these hard brittle rocks that you find in EGS. Thermal spallation is another method. Basically, the idea behind thermal spallation is through the rapid application of heat, we induce high compressive stresses close to the surface of the rock. These compressive stresses, they drive fractures parallel to the surface. Eventually, once those fractures have reached a sufficient extent, the compressive stresses act to buckle that fragment, and it pops off as a small piece known as a spall. Now, the idea of using thermal spallation as a drilling technique is not a particularly new one. In fact, it's been around since the 1940s, when it was first used as a method for creating blast holes in taconite mines. Since then, it's been extended to a variety of different applications, and as well a variety of different drilling technologies, including technologies and applications for deep well drilling. And the advantages of using thermal spallation as a drilling technique is that it allows you to penetrate hard granitic basement rocks at a much faster rate than conventional drilling methods. Moreover, because you're using the heat, it's a contactless drilling method, so you get less wear and tear on the drill bit. As a result, you lose less time for tripping or equipment replacement. Finally, unlike conventional drilling methods, which are essentially unidirectional with some sort of twisting, with thermal spallation, you can redirect that heat source out to the side, and in that way you can use it to create cavities or use it to create slots, which may improve the hydraulic properties of your geothermal well. So we have been working with Potter Drilling to develop a suite of models to simulate their thermal spallation drilling technology. And we've been looking at different models on different length scales. Today I'm going to concentrate on just one of those models, the grain scale model, looking at modelling some of the processes involved in generating spalls at a very small scale. So in our grain scale models, we take a representative volume element of the rock that we're interested in simulating, and we have a particular method of generating these rock microstructures that enables us to reproduce the grain scale distribution for the individual mineralogy exactly. And then we can assign different constitutive properties and indeed different constitutive models to those individual grains depending on what we want to simulate. Once we have that representative volume element, we can then apply a heat source to one side of it, allow that heat front to propagate into the rock, and as it goes in, it initiates fractures, so we can see where these fractures are initiated from the thermal stresses, and we can also see how those fractures propagate and the spall size distribution, or the spalls that are produced as a result. Once we've run these simulations, we can look at the spall size distribution that's produced, and typically what we see is the spall sizes follow a log normal size distribution. And what I've done here is I've summarised the results of over 100 different simulations where we looked at a range of different parameters, including hydrostatic pressure, lithostatic pressure, the microstructure, and also the effect of the applied temperature. And what I've done here is I've just plotted those simulations in terms of their applied temperature differential, and also the colour scale shows the ratio of the hydrostatic pressure to the lithostatic pressure. You can see from these simulations we get a variety of different sorts of behaviour. To start off with, we get a range of models that actually undergo very little or no spallation, which is indicated by the zero logarithmic mean. And then that typically occurs for low temperature differences. As the temperature difference increases, though, we undergo spallation, but then with increasing temperature, we find that the spall size distribution, the average spall size, tends to decrease, both with increasing temperature and the increasing ratio of pressures. So what we can infer from this is that as we're improving or increasing the energy in the system, both in terms of the thermal energy, but also the potential energy between the interior of the borehole and the lithostatic stress on the borehole, that energy is being spent not only in generating more spalls, but also in making smaller spalls, so it's being exhausted in making more fractures in a sense. What's interesting about that is the locations at where these spalls become initiated. So what we can do is we can take our simulations and we can run several simulations with the same microstructure, but applying different temperatures to that microstructure and see where these spalls are initiated. What we find is these spalls don't just initiate at random locations, they follow a certain pattern to them. In fact, we sort of see that they follow a set of critical flaws. So if we have a low temperature, we initiate spalls at points, at certain points inside the assembly, but then as we increase that temperature differential, we find that those same points tend to be the sites of spall initiation as well. Now, the reason why that is of interest is because it feeds in nicely with some existing models of spallation that are already used on the continuum scale, namely these Weibull statistical failure models. Now, what these models do is they postulate the existence of a critical flaw distribution within the rock body, and they use that in order to introduce more heterogeneity into these continuum scale models. And they've been used with quite some success to predict how spall distributions relate to penetration rates for these sorts of thermal spallation drilling technologies. And there's a couple of drawbacks, however, which are associated with these Weibull type models. One of them is that they're essentially empirical models. So in order to run them, you need to conduct a range of experimental simulations in order to calibrate them against what you're seeing in the lab. And moreover, while they postulate the existence of this distribution of critical failure sites, they say nothing in particular about their nature. So one of the things we're interested in doing is seeing if we could run our simulations, so see if we could find anything out about what the, or if we could say anything about what these critical sites look like, about the nature of these critical sites. In so doing, we also were looking, or started to be interested in some other models of spallation in other materials, in particular in high-performance cements. Now, spallation in high-performance cements is of concern because it's been seen in a couple of tunnel fires, for example. But it follows a slightly different mechanism to what's thought to occur in granites. So basically, in cements, the process is thought to be that you heat up the cement face, the heat front propagates into the cement, but now you're vaporizing the water that's contained inside that cement. As you vaporize that water, it increases the pressure within the cement, and this causes the spall to break off and pop off the surface. Now, this sort of mechanism has been largely ignored in granites, presumably because of their extremely low porosity. But what's interesting about the porosity in granites is, even though it is very low, it's not evenly distributed throughout the granite body. You can see that it's greater in certain grains, like plagioclase, for example, can have quite a high porosity compared to the overall porosity of the granite. And what's more, it's heterogeneously distributed, so you can find it's more prevalent at particular sites within the granite and particular grain boundaries, which we would also expect to be sites of weakness within the grain body itself. What's more, it's not just the porosity that drives this vapor-driven spallation, it's the low permeability. It's the ability to build up that vapor pressure that assists in creating spalls. And granite has that in spades, obviously. So in order to see what effect we would have on running on our microstructural simulations, we ran a series of simulations where we introduced porosity into the granite assembly. So we ran a suite of simulations where we took the same microstructure, both with no porosity, and also where we introduced porosity at 0.1% and 20 micron diameter pores. And what was interesting about these simulations is we could see that there was a change in the pattern of spallation. So unlike previously, where we're seeing essentially the same sites being spalled as we're increasing the temperature, now these spallation locations started to change. And when we looked into what that was going on, we realized that the addition of microporosity was both reducing the spall size distribution and also the extent of damage within these simulations. And what was happening is the micropores were serving as sites for fracture initiation. So the heat front was penetrating in, the micropores were now starting to expand and contribute to that local compressive stress, but also because they were essentially sites of heterogeneity, they were sites of fracture initiation. These fractures then started to propagate, but their propagation was assisted by the expansion of the fluids within those micropores. So what we see is a slightly different picture of what's going on inside these, this granite body than what we previously thought was happening with both the stress-driven spallation or with the vapor-driven spallation. It's kind of a hybrid of the two modes of spallation. So essentially, we see a mode in which we are both heating up the micropores and they are contributing to the buckling risk of the spallation within the granite body. So in summary, we've developed a number of models of spallation on several different scales, both looking at the system scale but also the grain scale. And we've been using that grain scale simulation to sort of help us fill in some of the missing details about what should happen at the larger continuum scale. What those simulations show us is they provide evidence for some existing models of spallation, namely these Weibull statistical failure models. But they also tell us some ways in which these Weibull models can be improved, namely by accounting for the effects of microporosity, I should say, on spallation events. So I'd like to conclude by thanking our sponsors from the Geothermal Technology Program and Potter Drilling for their ongoing collaboration. Thank you very much.
We have a couple minutes for questions. Any questions? Can't see.
Oh, there seems to be one up the back there.
Please.
Yes, it does. I think the question was, does the model simulate fracture initiation and propagation? That's correct. Yes, it does. So it's a...
More details.
Oh, more details? Yeah, it's... Sure. It's a Eulerian model, and it uses a damage criterion to simulate fracture initiation. The Eulerian model that we use allows us to simulate... so typically what happens in these spallation events is you get fracture initiation at the boundaries between grains, So you need some way to simulate that initiation at those boundaries, but then the fractures propagate within the grains themselves. So the advantage of using this Eulerian model is that we can simulate both of those sorts of modes. It's not just a failure along grain boundaries, but we also can propagate within the grains themselves.
All right, thank you. Our next speaker is Randy Setgast from Lawrence Livermore Lab, and he's going to talk about simulation of hydrofracking in 3D networks. If you want.
Gotcha. What's that? Are we short on time? Okay. Thank you for coming. My name is Randolph Setgast. My co-authors or people who have worked on this are Scott Johnson, Stuart Walsh, Josh White, Peng Cheng Fu, Eric Herbold, Rick Ryerson, and Teraby Anton. They're all part of the Atmospheric Earth and Energy Division at Lawrence Livermore National Lab. So what I'm going to talk about today is the numerical modeling of the evolution of fracture networks. It's geared a little bit towards shale and gas recovery, but it can be applied to EGS systems. I'm going to skip that. So there's several tools developed by the recovery oil and gas service industry. We don't need to get into the specifics. There's Baker Hughes, Carbodynamics has Frac Pro, Schlumberger has UFM. You know, there's various tools. They all have their limitations. What we're trying to do is develop a set of tools with varying limitations, all the way from basic physics all the way up to fast-running tools. So what we want in the end is a fast-running tool to determine an optimal approach for hydrofracking a given site. So what's required from that is what data is needed to calibrate the tool, what are the errors and the error bounds associated with the site. You know, to start, you know, as a starting point, we need to have a good deterministic simulation capability to basically use as a computational experiment for calibrating all the higher level tools. So to that end, we're developing a deterministic computational capability for the modeling of three-dimensional hydrofracture, or 2- and 3-dimensional hydrofracture, but the push is for 3D hydrofracking. Geos is the name of the code. It's an open source, massively parallel code. It actually currently has finite element, boundary element capabilities, and discrete element capabilities. I'm going to be talking about today is strictly finite element capabilities that we're using to simulate the fully coupled flow and deformation in the evolution of the fracture network. You know, one of the goals is to basically apply fracture mechanics at the bench scale or in the lab, and we would like to apply fracture mechanics at near field scales, but as I'm going to show later, that's going to be fairly difficult. You know, we want to be able to simulate various methods of fracture stimulation. So, you know, you could, you know, standard hydrofracking is just pumping a certain pressure down there for a given amount of time. You know, how does varying the pressure levels, maybe pulse loading, affect the evolution of the fracture network? And finally, since we're at Lawrence Livermore National Lab, we have significant computational capabilities. So our target cost for production runs are about 85 teraflops. You know, on 12 hours of runtime, that's about 3.7 billion floating point operations. Okay, so I'm just going to get into a couple of the equations associated with our hydrofrac simulations. You know, this is the basic finite element method applied to the equation of motion. You have, you know, this is the residual. So it's your standard divergence of the stress integration over the volume of the continuum. Body forces and acceleration. I left out acceleration here. application of any cohesive finite element or cohesive fracture mechanics stresses along a subportion of the area of the crack, your standard boundary traction terms. And the one thing that may be a little bit different is the application of the fluid pressure along the hydrofrac crack right there. Okay. And for the flow solver, what I'm going to show today is basically, we use a parallel plate flow assumption. So we have this finite element mesh, and we break it apart, do topology change, and we flow, we do a fluid solve in the cracks that we generate. We can define the permeability. We can define the permeability of a face as such, where your alpha is your aperture distance, so it's alpha cubed. W is your width of the face, and L is your distance from the center of the face to the edge. So this is you can apply a mass flow rate from face to edge, apply conservation of mass on the edge, so you sum up all the faces, all the contributions from each face associated with an edge, apply simple EOS, and off you go. This is just the same equation in terms of a generalized trapezoidal method. What I'm going to show today is time explicit simulations. You can see the, well, I'll just skip that. Oop. How'd I go to? Okay, so real quick, the possible fracture approaches. When doing fracture mechanics at scales like this, we can try to apply cohesive zones or some sort of fracture mechanics methods at fine mesh resolutions and get mesh convergence as long as you have 3 active cohesive zones behind the crack tip. This would be fine for lab experiments, but at field scales, we really don't have a shot at getting the required mesh resolutions. We could also use displacement methods. So displacement methods, I generally term displacement methods as they take the displacement field behind the crack tip and try to associate some stress intensity factor with that displacement field. Problem with that is linear elastic fracture mechanics doesn't necessarily apply to rocks at high confinement. You would end up having to vary stress intensity factors with confinement, things like that. We would like to be able to model arbitrary crack paths. So what I'm going to show you today is hexahedral mesh with cracks along the element boundaries. That has problems associated with it. When you're trying to do arbitrary crack paths, you would end up getting stair stepping if you don't have nice planar fractures. You could apply XFEM-like concepts with partial volume integration to actually be able to cut through the elements. But that's a research topic in itself. Or you could try to basically take the elements, break them apart into smaller sub-elements using arbitrary polyhedral elements, which would be the most general approach, which is what we're going to try but haven't done yet. Okay, real quick, the statement I made about trying to model fracture or using fracture mechanics and cohesive zones at depth. This is basically what your mode 1 stress looks like at the tip of a crack for a depth of 1,000 meters and 5,000 meters. I've cut off, the asymptotic stress at some reasonable value of tensile stress. But you could see you would require elements on the order of, 1/10 of a millimeter. And at the field scale, if you actually had 1/10 of a millimeter element sizes, without significant AMR capabilities, you would just have an untractable problem. Okay, so I'll go over real quick the time explicit mechanics and flow coupling algorithm that we use for the simulation that I'm going to show. So the first thing you have at the beginning of the step, can you go back one? Yeah, that's fine. You basically, and this is kind of a 2D toy drawing, but you would basically have your crack in 2D. You have your pressures on the face facets, in between at time n. You could use those to perform a flow solve to get the mass at time n plus 1. You could deform the mesh using your standard Numark update. Then you could update the material state of the solid and fluid using a standard whatever material model you wanted and some EOS. Apply the fluid pressures to the solid faces and evaluate the fracture. Okay, real quick note, this is going to get a little bit computational here. Topology changes in a parallel code. So when you're doing mesh splitting in a parallel code, you're presented with significant challenges. So if you do the splitting sequentially through all the nodes, when you split a node, all edges and faces along the separation path are split as well. You know, when you're doing parallel communications, you have the concept of ghost and local objects. The problem is you can split your local nodes, and then you would be required to split your non-local ghost edges and faces. And if those are split on the other domain, your neighbor domain, at the same time, you can split them in different ways, which would mean you basically have an inconsistent topology across the mesh boundaries. So what we do to overcome that is we use a color map. I don't know why they call it a color map. We always just label them A, B, C, D type things. So, so basically, if this was your domain, you just had some rectangular domain, you would break that up, you know, on one, you have your domain, each of these would be like mesh partitions. So in this case, this would be a 4x4, a 16 partition problem. You would label each of them A, B, C, D, like so. You would basically only process the boundary objects on A, and you know, and all the other ones would be, all the other colors would be waiting. Once you finish processing and processing all the topology change required on the boundary for A, you would communicate that to B, C, and D, and then change their topologies as defined by A, and then go on to B, and so forth and so forth. Eventually, you would do the interior of the domain, and those are not subject to the limitations. In 3D, there would be 8 colors. Okay, so I get to show you one whole simulation today. This is a 3-dimensional fracture propagation through pre-existing joint sets. So basically, I've defined a 200 meter by 200 meter block. This is about a million element problem, 2 meter mesh size. We've defined a bunch of pre-fract or pre-fractures, pre-fracture joint sets. You basically just apply pressure in the borehole. You can basically will connect up to any pre-fracture joint sets. Now in EGS, you may not have a bunch of pre-fracture joint sets, but you can see that the fractures grow and connect any pre-fracture joint sets as you go. Just a quick note, quick scaling study that we did. So when you're doing any massively parallel simulations, you want to know how it scales. We're going to get up to processor counts of maybe 4,000, 8,000, 16,000 processors. And what this shows is we get a drop off in efficiency from what it is actually a 1 to 16 processors, and that's due to memory bandwidth on a single node. 16 processors on a single node will basically use the same memory bus, and then you lose about 50% of your efficiency. But after that, we have no loss of efficiency with increase in processor size. So we can basically run as big of a problem as we want and not worry about efficiency degradation. And in the field, when you do a hydrofrac, when you actually do a hydrofrac operation, all you have typically is microseismic data. So what we're doing is we can take the large heterogeneities, which are the fractures themselves that we're simulating with this tool. We can get those signals, and then we can try to get microseismic signals associated with the small heterogeneities that we're not modeling, using some sort of stochastic driver based on the material state surrounding, in each of the elements surrounding the fractures. Then we can use a wave propagation tool to propagate those signals to the surface and simulate, what we would see at the experimental field scale. So ongoing work. We have to implement a coupled implicit solver, so that would be quasi-static mechanics. So what I showed you was basically dynamic simulation that required 1 million time steps for 30 seconds. We want to be able to run a full hydrofrac simulation, which is on the order of hours, so that's not really feasible. So we need an implicit coupled solver, more natural crack surfaces, development of appropriate fracture approach for crack propagations at field scales, porous float or model hydrofrac fluid loss and resource recovery, or in the case of EGS, that would basically be the flow through the fracture network and the thermal flow into the fluid. A method for modeling proppant transport is in the works. And obviously, when you're dealing with any geologic systems, you want to worry about stochastic considerations. Having a stochastic driver to drive your deterministic simulations, and continue to extend the coupling with microseismic sources. That's it.
Any questions for Randy?
I don't think so.
I have a question later on.
Okay.
We go to the next speaker. Is by Dr. Wong. He's going to talk about basin-wide heat transport induced by earthquakes.
This is a talk about earthquake-induced transport in the sedimentary basins. And why earthquake would induce transport in sedimentary basins, and why is this important? Earthquakes can change groundwater flow, and which in turn can change subsurface transport. Groundwater transport can affect water supply and water quality, hydrocarbon migration and maturation, underground repositories, and engineered structures. And here's the outline. There will be a change of pace from laboratory and simulation-based studies to field-based studies. So we will first start with observations, and then followed by method, results, and concluding remarks. Okay, observations came from the change of temperature in wells in Taiwan after the Chichi earthquake. And the wells locations are marked by the open circles, and the epicenter of the Chichi earthquake is marked by the baseball field. And the wells with temperature measurement before and after earthquakes is labeled. And here it shows the change in temperature after the earthquake. And here we show the data on a change in temperature versus distance to epicenter. Except for these few outliers, most of the data shows a trend of increase from distances close to the epicenter of a drop in temperature up to -1 degrees to increasing away from the epicenter up to near 1 degrees. And if some of the scatters is a result of different depths of the wells. If we limit the well depths to, say, 150 meters, and then the trend of increase in temperature from the location close to the epicenter to locations away from the epicenter becomes clearer. And you can see from here, in the recharge area that is close to the epicenter, you have a drop in temperature, and away from the epicenter in the discharge area, you have an increase in temperature. And so what's new? Okay, first, such data is available for the first time. And then it shows surprisingly effective earthquake-induced transport, both in time and in space. Earlier studies focused on the recharge area near the upper basin rim, and here we studied the temperature change across the entire basin. We studied the change of temperature using the heat transport equation that includes both the conductive component and the advective component. And here we have Q sub x and Q sub z showing the x and z component of Darcy's flow. And to get the Darcy's flow, and we use Darcy's law and solve the groundwater flow equations for layered rocks. And here, K sub x and K sub z are the effective hydraulic conductivity of the layered rocks in the sedimentary basin. And we know that parallel to bedding, the effective conductivity, K sub x, is given by this relation, and normal to bedding is given by this relation. So parallel to bedding, the effective conductivity is controlled by the layer with the highest conductivity, while normal to bedding, it is controlled by the layer with the least conductivity. And earthquake change that relationship. During the earthquake, we have evidence to show that the vertical conductivity has drastically increased, and that changed the entire permeability structure and therefore the pattern of groundwater flow. Supporting evidence for this statement include field mappings of fractures, flooding of tunnels, decreased water levels in wells, and then decreased water temperature in wells near the epicenter. And so we simplified the conceptual model by this idealized post-seismic model. That is, in the recharge area, we have this increased recharge at the time of the earthquake, which recharged the aquifer, increased the flow to the sedimentary basin. And here we show a relation from that simplified model, the recession of the excess flow given by this relation. You can see the exponential dependence on time. And we use the post-seismic recession of water levels in wells in the area given by these dots in 3 wells here to estimate the hydraulic conductivity after the earthquake. Using the pre-seismic K from wells to obtain a steady-state solution as initial conditions for the post-seismic transient flow, and then use post-seismic K to estimate the groundwater flow and to get the Darcy's velocity, and then use the Darcy's velocity in the heat transport equation to get the temperature change as a function of time. And we use the finite element method to implement this calculation. So here we have recharge area, and here we have discharge area, separated by a distance of 60 to 80 kilometers. And here we also show the boundary conditions on each boundary. And we have 2 hydrological models. One includes only the alluvial fan in front of the ruptured fault, marked by C here. The other model includes also the very thick gravel bed deposited at the time of Pleistocene when the mountain building in Taiwan was ongoing in the aquifer. Okay, this is the first model that involves only the the alluvial fan in the model, and here it shows the model doesn't fit the data very well. And then we have the second model that has only the upper rim of the basin that is fractured. Okay. The model also doesn't fit the data very well. In the last model, we also include the thick gravel bed, but we have permeability enhancement across the entire basin. And the model results fit the data reasonably. And here we have two hydraulic conductivities differed by 1 order of magnitude. And here we show two models for two different hydraulic head. One is just a linear increasing with distance from the coast to the epicenter. The other one has a dependence on the distance squared. And the data is too scattered to differentiate these two models. So in conclusion, the fit to data by the second model, that is including the thick gravel bed and allowing basin-wide enhancement of vertical permeability after the earthquake, the data fit is acceptable, considering the data scattering and the simplicity of the model. The second conclusion is that large earthquakes can induce effective basin-wide transport. The model invokes rapid release of stored groundwater from higher elevation, deep circulation, and basin-wide enhancement of vertical permeability. The model is testable when detailed geochemical data becomes available. Thank you.
We have a lot of time for a few questions. Yes, please. How do you specify the specific storativity? Is that the question?
Okay.
How do you specify the specific storativity?
Okay. The specific storage is obtained from tabulated data for gravels, okay, for the thick gravel bed beneath the alluvial fan. Also, in the alluvial fan, we also have very thick, several hundred meters of gravel. So we used the specific storage of gravel and coarse sand.
I have a follow-up question on that.
Yes.
Actually, do you change also the storativity to the earthquake or not? Because if you change the permeability, you change the porosity, therefore you change the storativity.
Yes, that's a very good question. Okay. The permeability change we assumed, and that is supported by field evidence, is a result of the creation of thin subvertical cracks, okay, which has very little storage by itself in comparison to the storage of the gravel. So we didn't change the storage before and after the earthquake.
I have a question. The subvertical cracks that you're talking about, is there field evidence for those subvertical cracks?
Yes. Right after the earthquake, there was field mapping across the ruptured fault. And there is plenty of evidence showing the creation of subvertical cracks. And there's also evidence for increased vertical permeability by sudden downpour of water in tunnels. And there's also evidence from well water level that shows sudden drop in water level. And there's also evidence from temperature that shows water temperature has dropped, indicating downward flow, advection of water.
Was there data, say 6 months beforehand on water temperature to just look at possible normal water temperature changes in the aquifer?
Excuse me, can you repeat that?
You're showing data of temperature changes as a result of the earthquake.
Yes.
How steady were the temperatures before and then some duration after, are they steady temperatures?
Okay. Okay, the wells were located at different depths. Okay, and many of the wells has depths of more than 100 meters. And at that depth, the temperature very steady and independent of the precipitation on the surface and temperature changes on the surface.
All right, thank you very much. Our next speaker is Tom Bushek from Lawrence Livermore Lab, and he's going to talk about integrated geothermal CO2 storage.
Where's the pointer?
You step in on it. The pointer, you took it with that.
Pointer's where?
Here's the pointer.
Okay, great.
Thank you for being here. My colleagues work at Lawrence Livermore National Lab with myself. Also, Mike Cilia and Tom Elliott, who was recently at Princeton, are also working on this project. Tom Elliott is working on the geospatial survey of these resources in sedimentary basins. And Jeff Bielecki from the University of Minnesota has been working on the economic analyses and the pipeline analyses. So where's the clicker for? Okay, sorry. Yeah, all right, thanks. So geothermal energy production can be limited by insufficient working fluid or by pressure depletion, whereas geologic CO2 storage can often be limited by overpressure. By synergistically integrating these systems, they can be of mutual benefit to each other, possibly enhancing the viability of each system. By limiting the overpressure to reduce pore space competition, the affected geographic area, which is called the area of review, and the risk of CO2 leakage and induced seismicity. We can also provide pressure support for producing geothermal energy from this injection, possibly defraying the parasitic energy and water costs. We could also produce water, but reducing these parasitic costs. I got it now. So the basic concept is that by injecting CO2 in a permeable sedimentary formation, we can provide pressure support to improve the productivity of brine production wells. This goes through a binary cycle power plant. The water from this can either be used for beneficial use through RO treatment or saline cooling water, and the residual of that be pumped back into the formation, or the entire amount may go back into the formation. This shows the thickness of the sedimentary column above the crystalline basement, and we're only considering areas that have 1 kilometer or greater because you have to have 1 kilometer in order to store CO2 to keep above the supercritical pressure. And so this shows the resources across the United States, and we're also excluding areas that do not show up in the NatCarb database of saline reservoirs. I finally get this. So the feasibility of this concept depends on several attributes. We have to have a formation that can sufficiently trap and store the CO2. We have to be adequately close to large CO2 emitters. We have to have a high enough formation temperature. And also we have to consider what are brine disposition options. While we were focusing on CCS, we were looking at ways of trying to offset the parasitic use of water by capturing CO2. So we were looking a lot at using this water beneficially. More recently, with more of a geothermal perspective, we've been looking at re-injecting this water for pressure support and generating Artesian conditions within the reservoir to help improve energy production. Finally get it. So this is just showing CO2 injection in a formation with no brine production. We've considered deep formations. In this case, we're considering formations either 5 or 2.5 kilometers in depth. And we consider a stack of 250-meter thick formations, permeable formations of 100 millidarcy, and seal units of 10 to the minus 18 or 10 to the minus 3 millidarcy, going all the way up to the ground surface. We're injecting a large amount of CO2 in this example, 15 million metric tons per year, which is equivalent to 2 large coal power plants, or roughly about 3 times what the Chevron Richmond refinery puts out in a year. We're injecting for 100 years. what we find is that due to buoyancy, CO2 spreads over a wide area, and that the area of maximum overpressure occurs at the interface between the storage aquifer and the overlying cap rock. So the next thing we can do is, the next most simple thing we could do is by adding producers at the center, we actually pull the CO2 plume towards the center. These producers are spaced 5 kilometers from the injectors. We take the produced brine and we re-inject them into these brine injectors at the top of the formation. And what we've done is that we've changed the shape of that area of overpressure, and we've created 2 hydraulic ridges on the outside which contain the CO2, which confines lateral migration of the CO2. So, but basically what we've done here is not change the picture in terms of neighboring users. We still are injecting the same amount of fluid into this formation. So the next thing we consider doing is taking half of the brine that we're producing and injecting them in the next overlying permeable formation. And by doing that, we raise the pressure in that aquifer, and we reduce the pressure difference across the cap rock, which reduces the tendency for CO2 leakage through the cap rock. However, in this case, because we're still injecting the same amount of fluid in the formation, we still have the same far-field overpressure changes. So the next thing we considered doing is that we added lateral or a perimeter brine producers outside of the brine injectors. So now we have 4 rings of wells, an inner ring of producers, a second ring of CO2 injectors, a third ring of brine producers, and now the 4th ring of brine producers outside of the brine injectors. And by doing this, we can create a hydraulic trough which isolates the influence of this hydraulic ridge so that neighboring activities like shale gas producers will not be interfered with by this GCS operation. And this, of course, also reduces the risk of leakage and reduces the risk of induced seismicity. So if you're looking at time, we've considered a broad range of different pressure management options and can achieve a substantial amount of reduction in the overpressure overlying the injection zone. One of the interesting things we find is as we go to deeper and deeper formations and conditions get hotter and hotter, the peak pressures are continually declining because the viscosity of water and CO2 are decreasing, so the hydraulic conductivity is increasing, which reduces the pressure buildup. So I won't go into the details, but we considered various things like spacing the injectors further apart, changing how much of the brine we consume for beneficial use, and how many brine producers we put out of the perimeter. So one of the things we can consider is the pressure difference across a cap rock. What we find is that that pressure difference is given by the net fluid injection in the respective aquifers, and without reducing any of the brine from the total system, we can substantially reduce this overpressure and the leakage risk. In order to reduce this to 0, we have to consume the brine and not return it back into the formation. And this is showing the overpressure 70 kilometers away from this operation, what these various brine pressure management options can do for you. And so what we find is that in order for this operation not to interfere with its neighbors, you have to find ways of consuming the brine and not re-injecting it back in the formation in order to minimize the area of review. And so what we find is that we have to actually, in terms of kilograms, we have to remove mass. We have to remove more mass of brine than CO2 because CO2 is roughly 30 to 40% less dense than the native brine. So to achieve this, we have to have net mass injection ratios that are less than 1. So now, just reviewing, we've come up with this generic pattern which has a zone of interproducers, which are initially brine producers, which become eventually CO2 producers as the CO2 breaks through. A ring of CO2 injectors, a third ring of brine injectors, a 4th ring of brine producers, and in the overlying formations, we have the injectors and producers. And this type of a generic pattern can generate excess brine, which could be available either for feedstock for product water or for makeup water for pressure support to create artesian conditions, which can reduce or eliminate the need for submersible pumps. So this is showing the temperature and heat extraction conditions at the 8 inner injectors, producers rather. And what we find is that the breakthrough time for the CO2 increases with increasing temperature because the mobility ratio between CO2 and water actually decreases with temperature. The viscosity of water increases more with temperature than does that of supercritical CO2. So what we find is that the colder locations see CO2 at the production wells earlier than the hotter cases. What we also find is that when we're producing just water, the heat extraction temperatures remain very high. Because of the wide spacing, thermal breakthrough does not occur. So it's not until the CO2 reaches the production well that we see a modest thermal decline. The thermal decline, as I said, is modest because of the fact that CO2 has a lower heat capacity of water, and it takes a lot longer to reduce the temperature in the formation. And so if we're looking at how much heat we can extract, what we find is when we're producing just brine, we produce at a high heat extraction rate. When CO2 breaks through at the same mass flow rate, this drops off. However, if we were to increase the flow rate, which would be possible due to the thermosiphon effect and the lower viscosity of brine, we could have maintained a similar high heat extraction rate. So what we're seeing here is that how much CO2 we have to deliver to the site depends on how long it takes for the CO2 to reach the production wells. Once the CO2 reaches the production wells, we're now recirculating CO2, so less CO2 has to be delivered to the injection wells. And so what we find is that the net storage of CO2 increases linearly until that breakthrough occurs, and then that increase begins to decline with time. So with this particular system that I'm showing here, we have 56 additional brine producers, 28 in the lower formation and 28 in the upper formation. And we also find that because of the fact that we have this hydraulic ridge sitting around the CO2 injectors, the producers in the lower aquifer never see CO2 because they're protected by that hydraulic ridge. Whereas in the upper aquifer, the middle aquifer, these producers also never see CO2 because we're not injecting CO2 in that formation. So these extraction temperatures decline very, very slowly because of the wide spacing, and we can recover geothermal energy for a very long period of time. So this is moving on to what we can achieve from an energy production point of view. There's a lot of information here, but I'll try to go through it. What we're showing here is the initial resource temperature, and this is the temperature at 30 years. Now, this decline in temperature that you see isn't actually thermal drawdown. It's due to the fact that we had our brine producers at the very bottom of the formation, these horizontal wells, and so we're drawing temperature from shallower regions at lower temperature down into the wells. So this initial thermal decline is not really thermal drawdown due to thermal breakthrough, it's just due to thermal mixing. But what we see is it's very slow. It's less than 0.1% per year, which is much lower than what you get in conventional hydrothermal systems, which is on the order of 0.5% per year. We also find that that if we can generate artesian conditions and eliminate the need for submersible pumps, we can dramatically improve the net power output by removal of these pumps. And this is particularly true at low temperatures. You can see here what I'm showing here is what fraction of the produced geothermal energy had to go back into the submersible pumps. For a formation at 100 degrees Celsius, we had to use a third of our energy just to drive those pumps to pull the water out of the formation. Now, as you go to deeper formations, this parasitic loss is less. So this, the benefit of avoiding the use of submersible pumps can also be useful in the levelized cost of electricity, as you can see here. And so in these scenarios that we were looking at here, we are actually producing an LCOE which is competitive with other energy sources, even natural gas for that matter, at these high temperatures. Now, a very interesting thing to look at is how much power do we produce relative to the amount of power. Now, in this case, this is the amount of power if we had coal generation that produced the CO2 that we're injecting in the first place. For this high temperature resource, we're able to produce 25% of the power that was generated by the CO2 that generated that CO2, which means that we have a very good opportunity to completely offset the energy, parasitic energy costs of CO2 capture and storage in those systems. So as we move forward in our program, looking at promising areas for geothermal exploitation, we're looking for areas where we can produce enough geothermal energy where we can justify the cost of capturing CO2 and actually making it financially viable to do without imposing a large tax on the cost of CO2. So you could also see, yeah. So anyway, so for our motivation here is to make have geothermal make geologic CO2 sequestration be financially viable. And in summary, because geologic carbon sequestration and geothermal energy have complementary needs, they can be synergistically beneficial to each other. We've developed a generic well pattern completed in 2 or more permeable layers consisting of 4 concentric zones of wells that can suppress CO2 migration, hydraulically isolate the operation from its neighboring operations, and reduce the risk of induced seismicity. This approach can also provide feedstock for generating product water. It can also provide makeup water for pressure support to generate artesian conditions, which can significantly reduce or eliminate the need for submersible pumps, which improves the levelized cost of electricity. These benefits can increase the net geothermal power output and reduce LCOE while enabling large-scale geologic CO2 sequestration. Thank you.
Any questions for Tom? Please.
Tom, is there anything to be aware of by injecting CO2 into a geothermal reservoir, basically? Are there any geochemical reactions to be aware of by carbonating the fluid?
I'm not a geochemist, and my colleagues at Lawrence Livermore and elsewhere have been working on that problem. We heard a talk earlier today, the first talk at this session, also talking about it. Yeah, there certainly are issues, and I think there are ways of dealing with that. I think I could talk to you at the break about. I have some ideas that actually might be patentable that could reduce some of these issues.
That sounds great.
Yeah.
Any other question? All right.
Thank you.
Let me get the.
Oh, of course you could use that.
Our next speaker is from New Zealand, and her talk is going to be "Don't Waste Your Energy: Model of Sustainability of Direct Use of the Tauranga Low Permeability Reservoir."
So renewable energy is of increasing interest around the world, and geothermal, where it's available, has a strong advantage because it's not dependent on the weather. It doesn't need sun or wind or rainfall for hydropower. However, geothermal systems aren't infinite. We only have a certain amount of hot water in each system. And so before using them, we need to look at the heat and fluid potential of a system and what the effects of withdrawing hot water would be. Geothermal is quite a significant energy source in New Zealand. It already accounts for 19% of total primary energy and 13% of electricity production. This is going up, and low temperature is becoming quite a big focus as high enthalpy just isn't always available, and also technology is becoming cheaper and other energy sources are becoming more expensive, so it's becoming more economically viable. It's already used for a range of uses in New Zealand, including direct heating, bathing, greenhouses, drying timber, and this is a fisheries outside my office in New Zealand. So I'm going to present a field in New Zealand, the Taupo volcanic zone, which you can see outlined in red here, is the main host of the high temperature springs and the electricity producing geothermal fields. But there are low temperature resources located pretty much across the country, and I'm going to focus on the Tauranga geothermal field, which is on the north coast of the North Island of New Zealand. It's located right under a city with a population of 120,000, making it the 6th largest urban centre in New Zealand. There are quite a few springs, up to about 40 degrees C, and wells down to about 700 metres that have flowing hot water of about 67 degrees C. So there's a pretty good low temperature resource, but there would never be enough for electricity production. So I've used a numerical simulation to answer two main questions. How does the heat flow through the system, and how sustainable is the current use? And to do this, I've used a specialized code called TUF2, which is based on physical laws of heat and fluid flow, primarily an adaptation of Darcy's law. And it can deal with different phases and components. In this case, I was just dealing with water and air. And on the bottom left, you can see the geological and geographical map of Tauranga, and on the right is the TUF2 grid that created using leapfrog geothermal. So the Tauranga model covers about 30 kilometres by 40 kilometres, which is the area in the centre of the model where there's a finer grid. The entire grid goes out to about 70 kilometres by 130 to make sure that boundary conditions don't affect the area that we're interested in. The model trends northwest-southeast to follow the coastline, and the main data that I calibrated against is well temperatures. So we've got 387 wells in the area. Most of these are groundwater wells that just have one temperature recorded over the last 40 years. So it's hard to know how much error is associated with them. And therefore I focused on the 17 wells that have temperature profiles with depth, which could give us a much better idea about whether the system was conductive or convective and that sort of thing. So here you can see the actual model. It's pretty simple. There's a thin layer of sediments with up to 2 kilometres of volcanics underneath. We don't have much data in the area, and what we do have suggests the volcanics are pretty much all ignimbrites. So I just treated that as one unit to keep it simple. On the top right, you can see the upper boundary condition. So over half the model, there's water with a hydrostatic pressure gradient. The other half is land with atmospheric pressure and temperature. And over the land, I also injected 5% of the annual average rainfall, which is based on measurements in the area. And the main thing that we wanted to determine and that sort of controlled the model was the heat fluxing through the system. So I varied quite a range of parameters, but the main two that it was sensitive to were the thermal conductivity and the heat input in the base of the model. And now I'll talk you through some of the results. So this shows the Tauranga area, and these are all of the individual temperature measurements that I had. So I've put in here the 17 wells that I calibrated against, and then the other 370 that I then used to sort of compare and just to check the model. And so starting with a cross-section to the northwest, you can see that we got a pretty good match between the profiles with depth and the isotherms. So each of the bubbles is a temperature. The darker the blue, the cooler it is. And then the isotherms are at 10 degrees C intervals. And stepping through the model, I could get a really quite nice fit between the well temperatures and the model temperatures. There was quite a lot of scatter in the individual point measurements, but overall it was pretty good. And just some basic statistics, there were some quite big anomalies up to 27 degrees C and down to minus 42 degrees C between the measured and modeled data. But on average, there was just 1 degree C difference between them. So I was quite happy with that, considering that's over the 380 wells. So here we can see the heat input, and the red is the highest heat input, which was 300 50 milliwatts per meter squared. The blue around the edges is about 55. That's the background rate for this area. And this is overlaying the geological map of the area. And there's a couple of domes, which you can see here and here. And previously, it's been hypothesized that those are the heat source for the area. But my model suggested the main heat source is actually further to the north. And the wells that data supports that pretty well. So I'm not quite sure what the actual heat source is under Tauranga because there's nothing obvious from the geology there. So this just shows the heat that's fluxing through the system, and it's quite focused right in the center under Tauranga itself, but there's also some rising heat that's sort of driven by the rainfall coming down off the mountains as well. So what I wanted to do is to use this model to look at the future scenarios based on current usage of the system. And currently there's 3 different main uses, which is commercial for swimming pools and fisheries, which is all year. Then there's irrigation for farms, both to provide water and to prevent frosts. So that's about 5 months a year. And then residential for heating houses. And a lot of people in this area are quite rich and have their own sort of hot pools and swimming pools in the backyard that are geothermally heated. So that's about 3 months of the year. And unfortunately, we don't have actual usage data, but we have estimated usage and consented. So I modeled a range of scenarios to see what this would do. And the gold line is the largest well in the field, which is the fluids withdrawn at about 80 kilograms per second. And the blue is just an average producing well. And you can see that the temperature doesn't drop too much on sort of average wells, but with the large well, it lasts for about 100 years, and then the temperature drops quite rapidly, and that well and the area around it actually completely cool down, and the well dries up, basically. When you double the estimated use, which could well be happening, the story is even worse. After about 60, 70 years, that well's dried up, and the pressure has dropped in all the wells. And this is the current consented values, which basically the local council didn't have any idea of what sort of numbers to put. So, and that's why they've asked me to do this. And you can see that if people did use their full consented amount, it would be pretty terrible. Like basically the whole system would die after about 8 years. I wanted to see if the story was any better if we just shut off that one big well. So the gold line is now just a background cell that has nothing going on. And here you can see that the pressure drops in the producing wells, but only by quite a small amount, and it restabilizes. And in fact, this model ran to steady state. And it's the same with twice the estimated use. So without that one big well, the system can basically be used indefinitely. But again, with the consented use, it's just too much. Any of the producing wells result in pretty much the whole thing just cooling down and shutting off. So we need to be careful about how we use these low-temperature geothermal systems. And modeling is a powerful tool to actually put some numbers on what we let people take out of the systems. They show that in Tauranga, current usage is sustainable in the medium term, about over the next sort of 100 years or so, but with not too much difficulty, we could make it fully sustainable. However, the current consented usage is just never sustainable, and this really needs to be looked at. And I'll just leave you with a thought for the day, or at least for the break. Thank you.
Any questions, please? I have one. When you did the comparison between your model and the single measurements in those wells, did you take like a depth average temperature, or what kind of temperature did you?
No, each of the individual measurements was plotted at the depth that it was measured, which was generally the bottom of the well. Yeah, and then plotted against the actual depth that the model was suggesting.
All right. Any other questions? All right. Well, thank you very much.
Thank you.